All right, Chapter 7, Basic Trigonometry here. We're doing the whole thing. I think you should have seen most of this chapter before, so let's try to get through a quick interjection. I forgot to mention this when I was shooting the video earlier. The word trigonometry comes from Greek, meaning the measurement of triangles. And in fact, trigon is what a Greek would have called a triangle. We use Greek actually for most polygons names. In fact, for 5 sides or above, we say a pentagon, a hexagon, and so on. Yet for 3, we say triangle, and which trigon is literally triangle. But however, for 4, we say quadrilateral, which comes from Latin for 4 sides. This is just one of many instances in the English language in which we came up with these names somewhat ad hoc back in history, and we just weren't consistent with it as we moved forward in the development of mathematics. If we had been, we surely would have called a 4-sided plane figure a tetragon instead. Anyway, back to Chapter 7. Starting off, the basic trig ratios, you should know how they're defined based on a right triangle with opposite, adjacent, hypotenuse, and all that stuff. If you like to remember it with SOHCAHTOA, that's cool. If you don't, I don't really care. But you got to know these trig ratios for sure. And we should also notice that tangent is equal to sine over cosine. All right, and we can use these trig ratios to, or we can figure out what they are based on a particular triangle if we know its sides. Awesome. We can also use them to figure out unknown lengths of sides within a triangle. All right, so pause and read through these if you need to. I think it's pretty straightforward, so I have nothing to add to it. Let's move on to section B, which is about using trig ratios to figure out a missing angle when we know 2 of the sides. So in this case, we've got the opposite side and the hypotenuse. So we know that sine is the trig ratio that uses those two. So we've got sine of theta is equal to 3 over 4, and we need to undo that sine in some way. Now sine's not a number, so we can't like divide by sine on both sides. But what we can do is we can use the inverse function of sine. Now, we have not officially discussed inverses in this video series yet, so we're not going to go into the details here. For now, we're just going to say there's a thing we can do on our calculator that undoes the sine function. It looks like this. It looks like an exponent, right? Sine to the -1. It's not an exponent. This does not mean 1 over sine of 3/4. It's a whole other thing, which we'll get into more details later on about, all right? But anyway, we just type this into our calculator, and we'll get an answer. I'll show you how to do that on ours right now. On the calculator screen, we press our trig button, and it's literally right there. Ta-da! And we see that we could use inverse cosine or inverse tangent just as easily if we had their sides given to us in the triangle. In fact, if we knew all 3 of the sides, then we could have used any one of those 3 and we'll get the same answer every single time. So all that we need to know for right now is that we use the -1 thingy whenever we want to figure out what the angle is, and it's called the inverse sine or inverse cosine or inverse tangent. And you might have seen that labeled as arc sine or arc cosine, arc tangent. Those are just other names for the same thing. They tend to be used more in continental Europe, in my experience. I have no idea what's popular in South America, Africa, or Asia, but anyway, it means the exact same thing. Okay, section C is just about like problem solving with various geometrical shapes. So you should be generally familiar with special types of triangles and special types of quadrilaterals and knowing what all of their properties are. Okay, so like in a square in the rhombus, we have diagonals that bisect each other and are perpendicular to each other. That's really important. We don't get that in a rectangle, and we don't get that in a parallelogram. And a kite, we have perpendicular diagonals, but they're not going to bisect each other. These two actually do bisect each other, but or that particular diagonal is bisected, but the other one clearly is not. Anyway, we should be able to use that and some basic trigonometry to answer some questions. We won't get into too much of that here, though. We also have some circle theorems that we should know. So first one here, when we have a tangent line, which is a line that just barely touches the circle at one point, that's always going to be perpendicular to the radius that goes through that same point of contact. We should also know that if we have a semicircle, any angle inscribed in a semicircle is always going to be a right angle. It does not matter where that angle is. That's a right angle. That's a right angle. They're all right angles. And then finally, down at the bottom, if we have a radius, well, if we have two radii and then a chord connecting where they touch the circle, so we've made a segment down below, right? Green area is a segment. Another radius, which would bisect that chord, is going to have to be perpendicular to the chord itself. Okay, so we should just know all those geometry theorems, and we should be able to use them. But none of the problems are particularly interesting, so I'm not going to go through them here. We'll work on those in class. Moving on to section D. Okay, just some vocabulary here. An angle of elevation, if you see that in a problem, it means it's an angle looking up from a horizontal line. And angle of depression is looking down from a horizontal line. Also important to note, if we have 2 points at different heights, the angle of elevation looking up is always going to be equal to the angle of depression looking down, because of course we have here 2 parallel lines cut by a transversal, and we have alternate interior angles which must be congruent. The rest of section D is really just some word problems of various types. Some of them have these words, angle of elevation, angle of depression. Some of them don't. Section E are more word problems. Now, the previous HL curriculum, if you have older siblings, friends, enemies, etc., who took that, bearings were not a part of it. Bearings do appear in the new course syllabus, so I think we should talk about them. These problems are always going to have to do with like maps or people walking around in the wilderness or something, because I don't know, I feel like you'd have to be a Boy Scout to know what a bearing is. But all it is it's an angle measured from north going around clockwise, which is kind of weird because usually in mathematics when we measure angles we go counterclockwise, but for bearings we go clockwise. Okay, and they're usually given with 3 I don't want to say that that's 3 significant figures, but they're given with 3 digits. So that 48 degrees is written as 048 when we're dealing with bearings. If you give an answer as 48 degrees, you're fine. All I'm saying is that in a question you might see a number that looks like that, which looks kind of weird, but it's nothing to panic about. That just means 48 degrees, okay? If you've got 2 locations, so in this case like town A and town B, the bearing from one to the other, they're going to differ by 180 degrees, as we see down here. It's like 48 plus 180 is equal to 228. And that's always going to be the case. But look, whether it's a word problem from section D or a bearing problem from section E, all you got to do is draw the picture and label stuff, and it's fine. Okay, it's just basic trig, nothing to worry about. Final section F, we go into 3 dimensions. Oh my gosh. And we're going to try to find the angle between a line and a plane. Now, a line might not be in the plane. So the image we're given here is that of a sundial. So this circular part, that's flat. So we can imagine that that's lying on a flat surface of a plane. The sundial itself, this is a line sticking out of the plane and actually then travels through it in the other direction. Okay, so that's not in the plane, as opposed to, say, this line here, part of that shape. That's in the plane because the entire line is it's in the plane. I don't know how else to say it. Anyways, when we talk about finding the angle between a line and a plane, we mean if we were to imagine like the shadow, if we had a light directly above this sundial, then the shadow of that green line would lie directly underneath the physical component itself. And that is known as the projection of the line onto the plane. And so the angle that we're going to end up measuring here is the angle between the line itself and that of its projection. That's really simple. It just, I don't know. The word projection might be scary to some people, or thinking of 3D can be intimidating at the first time you do it, but otherwise this is really straightforward. So here, let's look at some stuff real quick. So this is a two-part question. Part A, the answer is down below, and that's pretty straightforward, I think. We're trying to find the angle between the base plane EFGH, and that's the bottom. So we want the angle between that and a particular line AH. Okay, so that's AH, is that right there? Well, clearly, if the projection of AH onto that plane, if we imagined its shadow, it would just be EH. And so then that's an easy angle to calculate. This was a cube to start off with, so that means that this front face here is a square. So that angle is obviously going to be 45 degrees, but you could think of it in terms of trigonometry, as we see there as well. For part B, when we're talking about the line BM, that's a little bit more complicated because, well, BM is from here to there. So where is the projection of BM going to be? It's not too hard, but the first time you think about this, it might be a little challenging. Well, it's going to go from M, obviously, because M is on the plane, to the point that's directly below point B, and that's F. So that's going to be the projection of BM. And we see that here. So we just need to figure out what that angle is. They've labeled it alpha over down here. And so we just need to work out a couple of lengths. Well, we know that this length here has to be 12. We know that this length is 6 since M was a midpoint. From there, we can figure out what the length from F to M is. And then once we know what that is, which ends up being the square root of 180, then we know that this height here is 12, and then we can use inverse trigonometry to figure out what the angle alpha is. That's all this chapter is about. Like I said, I certainly think you've seen basic trig and inverse trig before, so nothing really to worry about here, except maybe some word problems, Mike Dory for loop or whatever, but we're going to practice those together. So that's it for Chapter 7, which again is just the most elementary basics of trigonometry. But we'll see as we move throughout the course why trigonometry is really one of my favorite areas of mathematics. And that's because it's really the first place where you, as a student, get a first row seat to see how different areas of mathematics which appear at first glance to be wildly separated from each other actually interconnect in just a beautiful and cohesive way. We start here with right triangles, we move on to non-right triangles, and then to circles, and then to waves, which have applications all over the place in physics. But at the same time, we have algebraic identities and equations, and it mixes in well with quadratics and all sorts of other stuff too. And I can just remember being excited as a student to see how all of these ideas came together in trigonometry. And I also remember being excited to see how some students around me had difficulty at it, whereas I was good at it, but maybe that makes me a bad person. I'm not sure. But anyway, if you're watching this, you're excited about it too. So, we're in good company together. Anyway, this idea of the interconnectivity of different mathematical concepts reminds me of a quotation by French mathematician Henri Poincaré, whose name I am pronouncing incorrectly, who said that mathematicians do not study objects but relations among objects. And this quotation is probably more profound than you may realize, because if you stop to ask yourself, just what exactly is it that mathematics is about? You'll find that throughout history there's been an abundance of suggested possible answers to that. And this philosophy of mathematics is, of course, all on its own. And you can surely find some interesting videos out there. I have a book in my own classroom library that you're free to borrow anytime you like. And I've always been somewhat of a fan of the idea that mathematics is about structures and relationships. Anyway, as is so often the case, I'm rambling on here, so that for now is the end.